Alrighty, now that we've learned how to times two matrices together when possible, that gives us more tools to work with matrix algebra and like hectic equations like this. So what we need to do before we try and work with this is to define the number like 1 in a matrix, because there's a really important property of the number 1, and that's if you take a number like 762 times 1, you actually get back to what you started with. Or if you do 1 times 762, again, you get back to what you started with. We need that equivalent thing in matrix form. So we already have the equivalent of the zero matrix. It looks like that. Or if you want a slightly different size zero matrix, it could look, I don't know, something like that. But the point is the zero matrix is just a whole bunch of zeros. But it turns out the identity matrix, the way that we construct that is we just do ones all down the diagonal, and then we just do zeros everywhere else. So you get something that looks like that for the identity matrix if we're talking about a 4x4 identity matrix. But if you're talking about like a 2x2, it's going to look like that one, or a 3x3 will look like that one. This is essentially our equivalent of the number 1, and it only works for square matrices. So every time you see I, it's going to be a square, not a rectangle matrix. And it satisfies these two equations, which is really important. If you times by I, you get back to what you started with, and it doesn't matter what order you do that in. Really important that both of these are true, because as you might remember from last time, it actually does matter what order you times matrices in. So just because this top one is true does not guarantee the bottom one is true. Have to be very careful. Anyway, so we got all these matrix algebra rules. I want to make really important note of the last one. A to the n exists only if A is square. And that's just because if you have a rectangle matrix like this, which is a 2x3, and you try and times it by itself, like to square it, you're going to be doing a 2x3 times a 2x3. And those middle numbers don't match, so impossible. So if you want to do a matrix squared, it has to be a square matrix to start with. So we're going to expand and simplify this. We do know that FOIL works, but we're not sure whether or not that perfect square formula works. If you remember from earlier on, we had a plus b squared equals a squared plus 2ab plus b squared. It's a question mark as to whether or not this will work with matrices. But we do know for sure that FOIL will work, so let's just expand it out like that. That first one's going to be a plus 2i with a plus 2i. We're going to FOIL this out. So we're going to get a times a, which is a squared, plus 2ai plus 2ai plus 2 and 2 gives us 4, so that's 4i squared. Now, I've really, on purpose, done something wrong on this line. I'd really like you to see if you can figure it out before I say what it is. So if you do want to do that, pause the video. The thing that I've done wrong is the third term here. We got it by doing 2 times I times A. So I should have kept it in the same order, 2 times I times A. Really important that you do that because it actually does matter what order you times matrices in. So let's see what this simplifies down to. A squared plus, this thing here is just 2A. Because a times I is just a, and then again 2a, and then 4i squared can stay just as 4i because I squared is I, just like our 1 squared is 1. All right, that becomes a squared plus 4a plus 4i. That's how this simplifies down. Okay, so next one we're going to do is a minus b squared. So again, we'll FOIL this out. So that's a take b times a take b. So we're going to FOIL. A squared is the first term, minus AB is the second term, just like that. Minus BA, be really careful of the order there. And then last term is take B squared. And it turns out this is completely done. As simple as possible. Could not get any simpler. And the reason for that is, in real numbers, you would be tempted to do this. So take 2AB. Sorry, that last one should be a plus. You'd be really tempted to do take 2AB there, but that would not be correct because AB and BA are different things in matrices. So you really have to second guess yourself whenever you're doing this expanding because you cannot swap the order you times things. So this is a question mark that we have. This does not work for matrices. You cannot use this formula, otherwise you'll get it wrong. And that's because AB does not equal BA. All right, last one we're going to do is something that looks like this. So a squared equals that. We're going to find a cubed and a4 just in terms of a and I. So a cubed is the same as writing a times a squared, and we know what a squared is. So we're going to expand that out. You're going to get 2a squared for your first term, plus 3ai. Then you're going to get 2a squared plus 3a, because a times I is just a. That's a cubed, and then if we want a to the 4, well, that's just a times by a cubed, and we can use our answer from before. 2a squared plus 3a. Actually, I could even keep going with this, couldn't I? That's my bad. A squared is 2a plus 3i, so that's 2a plus 3i plus 3a. So that's going to be 4a plus 6i plus 3a, which gives me 7a plus 6i. And you'll notice here that's actually the form they wanted it in. So k is 7 in LS6. Anyway, a4 is a times a cubed. So that's going to be a lots of 7a plus 6i. So that's going to be 7a squared plus 6ai, which is going to be 7a squared plus 6a. And we know what a squared is. It's 2a plus 3i. So that's 7, 2a plus 3i plus 6a, which is going to be 14a plus 21i plus 6a, which is just going to be 20a plus 21i, just like that. So that's another kind of thing you can do with this. In fact, it could be pretty fun. I'm not sure how this would work out, but you might even be able to make a conjecture about any power of a there.